Hi, I'm Dr. Eva Horvath, and this is part of the BocaPhysics series on electromagnetism. In today's lecture, I'm going to be discussing the solution of electrostatic boundary value problems in cylindrical coordinates. Let's begin with Laplace's equation. Reading this off, we have 1 over s times the partial derivative with respect to s of s times partial derivative of the potential with respect to s plus 1 over s squared times the partial derivative of the potential with respect to phi plus the second partial derivative of phi with respect to z. In order to solve Laplace's equation, I'm going to make use of the technique of separation of variables. So what that means is I'm going to assume that the potential has the form of a product of some function s, some function phi, and some function z. So my first function s is only a function of the variable s. My first function phi is only a function of the variable phi. And my last function z is only a function of the variable z. I plug this back into Laplace's equation. Since phi and z don't depend on s, I can pull those outside of the derivatives. And since s and z don't depend on phi, I can pull those factors out. And since s and phi don't depend on z, I can pull those factors out of the final term. And therefore, my Laplace's equation now has evolved into phi z over s times the derivative with respect to s of s times the function s, derivative of function s with respect to s. Second term is sz, function sz, over s squared times the second derivative of the function phi with respect to phi plus s phi times the second derivative of z, function z, with respect to z. We're going to divide everything through by the potential. So in other words, I'm going to divide every term by this function s, function phi, and function z. I now have a sum of ordinary differentials. We've got 1 over s, variable s, 1 over function s, first derivative with respect to fs of s times the derivative of the function s with respect to s plus 1 over s squared times 1 over phi times the second derivative of the function phi with respect to phi plus 1 over the function z times the second derivative of the function z with respect to z. Now last time around we were investigating Cartesian coordinates. You notice that each term broke apart nicely into something that's only a function of x, something that's only a function of y, and something that's only a function of z. See here, we've got z isolated. However, not only is the first term a function of s, but also the second term as well. So what I'm going to do first off is to tackle this final z term. And just as before, we assumed that it was equal to some constant. In order for this to vanish, we had a choice whether it's going to be minus k squared or k squared. As it turns out, it depends on the boundary conditions, but I'm going to just assume, for starters, that this is equal to k squared. And then I'll show you what happens if this term is equal to minus k squared instead. Okay, so let's solve this equation, this differential equation. And we've got two solutions. Solution is going to be a linear combination, I should say, of two terms. And you can either write this as hyperbolic sine, hyperbolic cosine, or in an exponential form. So I'm going to stick with exponential form for right now. Again, just as before, which form you chose, or you choose rather, depends on the kind of boundary conditions you have. Well, I haven't even specified a problem. I'm just basically writing out what forms the functions have to have. So I'm just going to leave it as an exponential to begin with. And therefore, my function z is going to be a linear combination of e to the kz and e to the minus kz. So far, so good. I've gotten rid of this one term. And now I'm going to consider the rest of my equation. I am now going to multiply every term through by s squared. Now, what you see is you've got the s terms by themselves and the phi term by itself. So in other words, we've got the sum of two terms that is a function only of s, and then we've got the third term that's a function of phi by itself. So I'm going to tackle this first, the phi equation. And you guessed, well, it's got to be equal to a constant, right? But whereas before we could choose whether that was going to be k squared or minus k squared, or depending on what the boundary conditions are, we didn't have any choice here. This has to be equal to minus n squared, and there's a reason for that. When you're solving this problem, okay, you're given boundaries and on the endpoints, generally speaking, and also on the sides of the cylinder. Okay? One thing I know about the function is that it has to be single value. So in other words, go all the way around. If I'm angular displacement is too high, I have to have the same, my function has to have the same value as before. So this has to be single valued. It's defined over the interval from 0 to 2 pi. And the only way that's going to happen is if this is equal to n squared, so that second derivative of the function phi with respect to phi plus m squared times phi has to be equal to 0. The solution is there. Or sine and cosine alone. Cannot have hyperbolic sine of phi or hyperbolic cosine of phi because those functions do not return to same value at too high. These functions do. Okay, so now we've got this term, we've got this term. So we plug my constants back in. That's equal to 0. So write this in a little bit different form. Just going to take the derivatives here, write all the terms out, and multiply through by the function s. My differential equation, second order, is s squared times the second derivative of s with respect to s, plus s times the derivative of s with respect to s, plus k squared s squared minus m squared times the function s equals to 0. This equation has a special name. It's Bessel's equation. And Bessel's equation has two solutions, Bessel functions. This is Bessel's functions written as a capital letter J with a subscript n times k s as the argument. And then we have the Neumann function as m subscript as a function of ks as well. I realize a lot of you have not yet taken math physics, but if you consult a textbook like Mary Boas's book, she talks about Bessel functions in this equation. I'm actually not going to go too much further with this analysis, but I just wanted to show you what's involved when you are solving electrostatic boundary value problems involving cylinders or pipes of finite length. Okay, so basically your solution is going to be in the form of some product, some linear combination of e to the kz, e to the minus kz, times some linear combination of sine and phi, cosine phi, times some linear combination of your Bessel function and your Neumann function. And again, some of these terms will drop out depending on whatever boundary conditions that you're given. I did mention before, or earlier rather, that I just chose k squared, okay? And so I was going to show you what was going to happen if this was equal to minus k squared instead. So I'm going to do that right now. So that's equal to minus k squared, and therefore the solution to this, I'm going to leave out a few steps here because I'm running out of room. Z then is going to be some linear combination of sine kz, cosine kz, and the phi equation won't change, but your Bessel function, or Bessel's equation, will be modified, and hence the name modified Bessel's equation. difference between my ordinary business equation and my modified one is that this final term is minus ks, k squared s squared plus n, whereas on the top I had k squared s squared is n squared. Modified Bessel functions, I sub n, k sub n, and once again, depending on whatever boundary conditions you are given, it's going to govern which of these two functions you use, or maybe you'll use both of them. Anyway, we are just writing these as j and ik, and they're actually summations. So again, if you're interested in looking into these kinds of problems further, I do recommend you consult Mary Boas's book. She's got a lot of examples with these kinds of problems. That being said, since we are doing undergraduate electromagnetism, not graduate level electromagnetism, we don't deal with problems of cylinders or pipes of finite length. We look at very long cylinders, very long pipes. The reason why I showed you this analysis is because I like students to have an idea of the limits of what they're doing at the present time. So in other words, when you're an undergraduate, well, you're talking about very long pipes, and you might be wondering yourself, well, what happens if you have a pipe of finite length? How does that change things? Well, it changes things because now you're going to have to deal with, or in those cases, you'll have to deal with Bessel functions, okay? So that's where you're headed if you take graduate electromagnetism, but after that brief digression, I'm going to go ahead and return our focus to very long pipes. And dealing with very long pipes, that means that we're going to ignore the endpoints and effects, and that means we're going to ignore AC dependence. So I'm going to erase most of the stuff to give myself some room. Final term drops out. Final product drops out. And I think I'll just rewrite this. Basically, we're dealing with a two-dimensional problem that has dependence only on the radial distance and also on the angle. Plug this fact that my potential is a product of some function s and some function v back into the Laplace's equation. And just reading off these terms, we have 1 over s, partial derivative with respect to s of s times partial derivative of sv with respect to s, plus 1 over s squared, second partial derivative of sv with respect to v. Well, v doesn't depend on s doesn't depend on v, so I can pull, in the first term, I can pull v out, and that'll just become ordinary derivatives. And I can pull s out of the second term, and that becomes ordinary derivatives. And I can multiply through every term by s squared. That will lead me to function, rather than variable s divided by the function s times derivative with respect to s of s times the derivative of s with respect to s, plus 1 over phi times the second derivative of phi with respect to the variable phi. Well, each of these terms only depends on one variable. The first term depends only on s, the second term depends only on variable phi, just like Cartesian coordinates, and just like when we're working through the three-dimensional example. This term is going to be equal to a constant, and in this case, this term by itself is going to be equal to a constant. V has to be, and consequently V, potential, both have to be single value functions. So therefore, this is equal to the constant minus m squared. We cannot use m squared because then that would lead to solutions in the form of exponentials or hyperbolic cosine and sine. And we want our function to return to the same value once we make one complete circuit. So in other words, it has to have the same value at 0 and at 2 pi. The only way that's going to happen is if the solutions of this differential equation here are sine and cosine. Okay? Phi is equal to some linear combination of sine m phi and cosine m phi. I'm going to tackle the first term. And I'm going to multiply through by the function s and do the derivatives, work the derivatives out. And the first term will therefore be s squared times the second derivative of the function s with respect to s plus s times the derivative of the function s with respect to s minus m squared s. Okay, so we don't have anything near as complicated as dealing with Bessel functions or Neumanns or modified Bessel functions. Turns out we can write down the solutions quickly. And let's look at the term m equals 0 first of all. M equals 0, that final term vanishes. So the solution here is perfectly valid, is if s is equal to a constant. So in other words, 1 basically, times a constant. Another possibility is if s is equal to natural log of s. Do this first derivative basically is 1 over s. So you have s over 1 over s, that's 1. This first term here, you'd have the second derivative of natural log of s, which is taking the first derivative, 1 over s again, and then minus 1 over s squared once you take the derivative again. So that's s squared over minus 1s squared, and that'll give you negative 1. So you have 1 minus 1 equals 0, so the equation is satisfied in the event that m is equal to 0. Now, what if m is not equal to 0? Solution can take two possible forms, either s to the m or s to the minus m. Your whole solution is going to be some linear combination of these terms, plus some linear combination of those terms, and possibly you'll have infinite number of terms in your series, maybe not, depending on the boundary conditions. The first problem I'm going to show you, the first example I'm going to show you, however, doesn't have any phi dependence. So any of this phi stuff will just drop right out. Let me raise some of this up to give myself a little bit more room. Potential is going to be some combination 1, natural log of s to the n, s to the minus n, times some linear combination of sine n phi, cosine n phi, and basically potentially summing over all an infinite number of n terms. In this example, I'm going to assume that I have two coaxial cylinders. Two coaxial long pipes. We come across the word long, very long, infinitely long. That's an indication that there's no z dependence in the problem. I'm going to assume that the inner cylinder is at potential VA, and the outer potential cylinder, or pipe, is at potential VB. The inner cylinder has radius RA, the outer cylinder has radius RB. There is no dependence on V here because the inner cylinder, the surface of the inner cylinder is VA everywhere. The surface of the cylinder, outer cylinder VB, or the outer cylinder is at VB everywhere. So what that tells me is that we're going to be considering problems where m is equal to 0. And we are seeking the answer to the question, what's the potential between the two cylinders? Well, if there's no phi dependence, then m is equal to 0. Basically, we're just going to be left with a possibility that Vs is of the form of some constant c times the natural log of s plus d. So s again here represents in cylindrical coordinates the radial distance. S is somewhere in there. In order to solve this problem, I need to apply the two boundary conditions. The boundary condition on the inner surface, inner cylinder, boundary condition on the outer cylinder. Inner cylinder or pipe, if you prefer, potential is equal to VA. And that's equal to constant C times natural log of the radius of the inner pipe plus D. The outer cylinder, the potential is equal to VB, and that's equal to C natural log of RB plus D. We've got two equations, two unknowns. I can solve for C readily. We just take the difference between these two equations. My constant C is equal to VA minus VB over natural log of A minus natural log of B. I can write a little bit more concisely as VA minus VB over natural log of A divided by RB. Now I'm going to solve for D. So essentially I'm just going to solve for D from this first equation and write out a common denominator for each of these. So let me read this off. D is equal to VA minus VB over natural log of RA minus natural log of RB natural log of RA. So that's my solution, but I'm going to write it in a little bit more symmetric form. So I'm going to multiply natural log of RA minus RB, numerator and denominator for VA. And see, this term cancels with this one, and we are therefore left with VB times natural log of RA minus VA, natural log of RB, all over natural log of RA minus natural log of RB. And that's your solution. We've determined what both of the constants are, and therefore plug the constants back in C, for C, natural log of S plus D. And that is your one-dimensional problem when dealing with very long pipes. Okay? Next example I'm going to show you does have angular dependence. We'll get to that right away. In this case, let's suppose that we have a very long pipe. And I'm given that the potential on the surface of the pipe has value E naught sine 2 phi. I want to determine what the potential is in the interior region and the exterior region. I'm going to first consider what the solution is inside. Well, the first thing you want to consider is that the solution has to be finite inside. So in other words, if it's finite, we can't choose some function that's going to blow up in the interior region, because natural log of S and S to the minus n diverge on the inside. They don't remain finite. those terms are going to be excluded from our solution. Therefore, in the interior region, possibilities are that it's equal to some constant plus m equals 1 to infinity of an s to the m cosine m phi plus p sub n times s to the m times sine of m phi. Now we're confronted with the same problem as when we dealt with Cartesian coordinates. We had a solution that had an infinite series, and there were coefficients, the values of which have not yet been determined. We're going to make use of the orthogonality of these functions to basically pull out what those coefficients are. So just as a writer, I'm going to write down what these relations are. So in other words, if we integrate over an entire period from 0 to 2 pi, some function cosine m phi times some function sine m tilde phi, that vanishes always, regardless of whether m and m tilde are the same or not. That's always going to be 0. I now consider what happens with the sines. Integral over an entire period of sine m phi and sine m tilde phi vanishes unless m and m tilde are the same, in which case that integral has value pi. It's a little bit different from cosines. Because as it turns out, we're going to have a non-vanishing result if m and m phi are equal to 0. But in the first case, if m and m tilde are the same, so in other words, we write this as a Kronecker delta, that integral is going to give the value of pi as long as m tilde are m, and consequently m tilde are not equal to 0. In the event that they are equal to 0, you wind up with a value of 2 pi. Okay, so let's determine what these coefficients are. Let's look at A naught to begin with. Let's see if I just integrate from 0 to 2 pi. And this is the value of the potential on the surface of the pipe. And I just integrate from 0 to 2 pi on the right-hand side. And we're integrating this summation term from 0 to 2 pi as well. By the way, I'm showing you the long drawn-out way of solving this problem. There's a faster shortcut that you can take once you once you get the trick. Anyway, if we integrate from 0 to 2 pi, this term is going to vanish, this term is going to vanish, and this term on the left-hand side will vanish as well. So the only possibility is for A naught to be equal to 0, right? This term integrates to 0. Both of these terms integrate to 0. The only possibility we'll be left over with A naught phi or A naught 2 pi, and with that is equal to 0, is if the coefficient A naught is equal to 0. How about the cosine terms? And to extract those, I'm going to multiply through by cosine m phi, m tilde phi. And by the way, I'm leaving out the A naught term because we just figured out that that was equal to 0. Now I'm going to pull the integral sign inside the summation. And let me read off everything here. So we have 0 to 2 pi of V naught sine 2 phi. Again, that's the potential that's on the surface of the pipe, times cosine m tilde phi, integrating from 0 to 2 pi. On the right-hand side, we have the summation from m equals 1 to infinity. Integral from 0 to 2 pi. This two terms in parentheses, we have an r to the m cosine of phi, cosine m tilde phi, and we have an r to the m cosine m tilde phi, sine m phi. Okay, so making use of orthogonality relations, this term on the left-hand side vanishes. Why? Because we know that integral 0 to 2 pi cosine m phi sine m tilde phi is equal to 0, regardless of whether m tilde and m are the same. So this is equal to 0. The second term vanishes as well. And we're left with this integral here, but we'll get a product delta out of it. Okay, so we've got our coefficient am, r and r to the m, and then this integral of the cosines together gives us a pi product or delta of m tilde, so that picks out one of the coefficients. But that has to be equal to 0. Well, obviously pi is not equal to 0, and our radius isn't equal to 0 either, so the only possibility there is for the coefficients a to all vanish. Now I've got to look at my b components, or b coefficients. Since we've proven that all the a's vanish, I'm going to go ahead and erase this because, fortunately, this whiteboard's not big enough. Last but not least, I'm going to multiply through by sine m tilde phi. And integrate from 0 to 2 pi. Well, we've determined that all coefficients a vanish. So on the right-hand side, I'm going to be left with summation m equals 1 to infinity, going from 0 to 2 pi, Bm 2 times the radius to the nth power, times sine of phi, sine n tilde phi, d phi. Now, lo and behold, we're finally wind up with some non-vanishing terms here. On the left-hand side, by our orthogonality relation, the only way this doesn't vanish is if this integer here is the same as this one, or rather this one is the same as this one. So in other words, we wind up with V naught pi times the product of delta of n tilde 2. On the right-hand side, we're going to wind up with another product of delta. Times pi. And again, that has the effect by multiplying through by the sign, has the effect of picking out one single term out of this whole infinite series. All the pi's cancel out. And on the left-hand side, we're told that n tilde has to be equal to 2, otherwise it vanishes. So the only surviving term we have then is b sub 2, and that's equal to v naught over r squared. Therefore, your solution, interior solution of a very long pipe, the surface of which is set equal to v naught sine 2 phi, is simply equal to v naught s over r squared sine 2 phi. There's an awful lot of work to write up, to come up with a rather simple expression there for your solution. I'm going to put a little less sign here to indicate we're talking about the interior solution. I mentioned earlier in this problem that there's a shortcut. Well, the shortcut is to recognize that if you have sine 2 phi or some kind of combination of sines or cosines, then your solution has to have that same combination of sine or cosines. By orthogonality, the only surviving term is going to be proportional to sine 2 phi. There won't be any cosines. And making use of that, I could have just looked at my general expression and saw, well, the only term that could possibly survive is when we have sine 2 phi. So that's going to exclude all the a's automatically. And I'll have basically v naught sine 2 phi is equal to b2 r squared sine 2 phi. So if you just jumped right in and realized that at the outset, you could have written down what the coefficient is, b2, right away, and solved your problem immediately in just a few steps rather than going through putting in all the bells and whistles. However, I like to go through that at least one time so students realize that we're not being arbitrary, just kicking out terms just willy-nilly, that there is a reason to it. But now that you know the trick, and if you have a potential that's set to some simple form like that, all you have to do is look for some linear combination that has that same form, okay? That being said, if we want to figure out what the exterior solution is, I know it's going to have to be proportional to v naught sine 2 phi. But I also know that it has to be finite as the distance away from the pipe becomes infinity. In fact, I want my potential basically to go to zero. So in other words, we want this to be equal to r over s. quantity squared. Okay. Okay. The next example I'm going to show you is where you don't have the potential specified on the surface, but you've got a surface charge density. So in other words, we'll say that's equal to some sigma naught. Times cosine through phi. The way you apply the boundary conditions in this case is a little bit different from the previous problem. So let's write down our solution. Let's look at the interior region. And let's write down an expression for the exterior region as well. In the interior region, we know that the solution has to be finite. So I'm going to exclude any terms that blow up along the axis. So that means I'm going to exclude natural log of s and s to the minus n. And the exterior region, I also want my solution to have finite form. It can't blow up as the radial distance gets bigger and bigger, so that means I'm going to exclude natural log s once again, and also s to the n. And here's my solution. So basically these two forms are the same, identical, except if we have s to the n up here, we have s to the minus n down here. Okay. So since we know that our surface charge density has a form of cosine through phi, we would expect that those are the only terms that would remain in your solution. Okay? But I said the boundary conditions are a little bit different here because we're going to make use of the fact that there's a discontinuity in the electric field at the surface of this pipe. And that discontinuity is equal to surface charge density divided by epsilon naught. Well, remember, it's the normal component that has the discontinuity. So therefore, the normal component of the electric field is equal to partial derivative of the potential with respect to the normal plus partial derivative with respect to the normal. And it's evaluated as s equal r. Remember again, electric field is equal to minus 3 in the v, which is why minus signs are reversed. Normal in this case is just normal to the surface of the pipe, in which case we are going to take the derivative with respect to s. So inside rather, our solution is going to be of the form of A3 r cubed times cosine 3 phi. Outside, our solution is going to have the form C3 r to the minus 3 cosine 3 phi. Okay. And let's see what else we can do right now. In addition to there being a discontinuity in the electric field, there's the potential is continuous across the boundary. So that means that, let me write this as S cubed and S minus 3. Okay, so in the interior solution we have A3 S to the 3 S cubed cosine 3 phi. Outside we have C3 S to the minus 3 cosine 3 phi. We also have continuity over potential. So that means this is equal to this at the surface, which implies that A3 is equal to C3 over S to the 6th. That makes life a little bit easier. R to the 6th. So this is going to be C3 S cubed over R to the 6th cosine 3 phi. And this is equal to C3, well, it's just the same as before, S minus 3 cosine 3 phi. Okay? So we've written down our general forms. Let me just go over this again. The solutions. So interior region, exterior region. The only difference between these is goes as powers of S to the n, and this goes as S to the minus n because we want it to be converged in the appropriate regions of space. We're going to apply the boundary conditions that there's discontinuity in the normal component of the electric field at the surface, and that discontinuity is equal to sigma over epsilon naught. And our differential equation here is going to be, or rather our boundary condition is going to be equal to minus partial derivative of the exterior region, exterior solution with respect to S, plus partial derivative of the interior solution with respect to S, evaluating the radius, is equal to sigma over epsilon naught. Okay. And by applying continuity of the potential, we were able to come up with a relation between A3 and C3. Okay. So I'm going to use C3 and plug it back in here. So in our exterior region, we've got minus C3 times minus 3. We're evaluating this at the radius, so this becomes r to the minus 4 cosine 3 phi plus C3. You take the derivative of this with respect to the 3, so that would be 3 times r squared over r to the 6th. Cosine 3 phi is equal to sigma naught times cosine 3 phi over epsilon naught. Each of these terms has in common a factor of cosine 3 phi, so that cancels out, and therefore C3 is equal to r to the 4th sigma naught over 6 epsilon naught And hence our solutions, plugging a constant in here, are equal to sigma naught over 6 epsilon naught times s cubed over r to the fourth cosine 3 theta. Our exterior solution is equal to sigma naught over 6 epsilon naught r to the fourth. Actually, that should be r squared. And in the exterior region, we have r to the fourth over s cubed cosine 3 theta. So let me just read it off again. Interior solution sigma naught over 6 epsilon naught s cubed over r squared cosine 3 theta. Exterior solution is sigma naught over 6 epsilon naught r to the fourth over s cubed cosine 3 theta. Notice this is continuous at the boundary, which is what potentials must be. And in this particular problem, there's a discontinuity because there is a surface charge density on the surface of the pipe. And that's how you solve this problem. So again, the important thing you want to notice is that in the previous example, we were able to just figure out what the potential was interior to exterior just by knowing what it was on the surface. Because we're given the surface charge density here, we have to make use of this boundary condition here in order to solve the problem. And that's how you do surface charge density problems. Okay? I have one final example to show you, and we'll get to that next. Okay. In this case, I'm going to assume that I have a very long pipe, top half of which is at potential V naught, and the bottom half of which is at potential minus V naught. I want to figure out what's the potential inside. Solution is going to have the form some constant, possibly plus summation n equals 1 to infinity. Again, since we're looking at the interior region, we can't have our solution blow up there, so that excludes any possibility of including the natural log of s or s to the minus n. So I'm going to again pull out AM and BN. You can realize for the boundary conditions, maybe you'll exclude one of these terms right off the bat, but I'm going to go ahead and do the math anyway. So on the left-hand side, if we integrate our solution, we're going to go from 0 to pi V naught dg plus pi to 2 pi minus V naught d phi. So in other words, we're just looking at trying to determine what A naught's going to be equal to. automatically, if you integrate from this over 0 to 2 pi and this over 0 to 2 pi, these terms are just going to drop right out. And what you'll be left with is the sigma A naught term. Okay, so you're going to wind up with A naught times 2 pi. But on the left-hand side, that clearly vanishes. So that tells you immediately that A naught is equal to 0. How about the cosine and phi terms? Let's look at those. I multiply my equation through by cosine n tilde phi. And I'm going to integrate from 0 to 2 pi. The surface of the pipe has value v naught from 0 to pi, and has value minus v naught, going from pi to 2 pi. When I do the math here, what I'll see is that I'll get v naught times sine n tilde phi over n minus m. And then over here, I'll wind up with v naught sine n tilde phi over n. So I have a minus and minus, which is a plus. Well, I don't need to go any further because if I have a sine of 0 or sine of any factor of pi, pi times an integer, that's going to vanish. So right away, I know that all the ANs have to be equal to 0. That just leaves the BMs, B sub m's. Okay. I'm going to erase this stuff again because I don't want to get over too far to the right-hand side of the board. So just by the nature of the boundary conditions, that means that all of our A's are equal to 0. Now I'm going to multiply through by sine m tilde phi. Okay, so on the left-hand side, we've got a sum of 2 terms. And when I do the math here, I'll get minus v naught cosine n tilde phi over n tilde. And actually, I think the previous line, I think I called it minus, but matters not. The signs are going to vanish anyway. So, but anyway, this is minus v naught cosine n tilde phi over n tilde. Evaluating from 0 to pi plus v naught cosine n tilde phi n tilde. So again, I just want to correct it. When I did the math in the previous example, I threw in an extraneous minus sign, but again, it didn't matter because those intervals led to 0 anyway. But here, we are not going to get 0, so we do have to be a little bit careful. This first term is going to be a cosine n tilde pi. Second term, v naught over n tilde. Third term, it's just going to be v naught over n tilde. Again, it's just going to be some integer times 2 pi, which is what cosine is always going to give us 1 in that case, and then minus v naught over n tilde cosine n tilde pi. Only way this left-hand side of the equation is going to be non-vanishing is if n tilde is equal to negative, or is equal to a non-number. Because if n tilde is odd, then we'd have cosine of pi, cosine of 3 pi, in which case we'd wind up with minus 1. Well, you're going to have minus 1 times minus 1. And we'd have minus 1 times minus 1. And that will add up these two terms, giving 4v naught over n tilde only when n tilde is on. On the right-hand side, we're integrating from 0 to 2 pi of the sine times sine, and our orthogonality condition gives us pi times chronic delta Fm and m tildes. That picks out one term. This is equal to this only when m tilde is on. When m tilde is even, v sub n will vanish. And I'm going to drop the tildes because m and m tilde are just dummy indices anyway. The coefficient v of n is equal to 4v naught over pi rn. In this case, in contrast to the two previous examples I worked out, it's going to have an infinite number of terms in the series. Solution potential is equal to summation n equals 1 to infinity pull the 4v naught over pi out of the integral times s over r to the nth power sine and phi. Only terms that contribute are those for which n is on. And that's your solution. Okay. And that's Laplace's equation, two-dimensional Laplace's equation in cylindrical coordinates using the separation of variables. If you're not familiar with Fourier's trick here, and if you'd like to learn a little bit more about Bessel functions, which we will get into further in this course, I do highly recommend that you consult Mary Boas' textbook on mathematical physics. She's got a lot of great examples to work through. So anyway, this concludes today's lecture. Next time around, we'll be discussing spherical coordinates.